Today I'd like to talk to you about very simple Bode plots. A Bode plot is the magnitude and phase of a transfer function plotted versus frequency. S is j omega, and transfer functions have a numerator and a denominator. And whenever the numerator of a transfer function goes to zero, we call that a zero. Whenever the denominator of a transfer function goes to zero, we call that a pole. And for instance, in this function here, what makes the numerator go to zero? S equals minus 1. What makes the denominator go to zero? S equals minus 10, or S equals minus 100. So the most simple thing to plot is when the transfer function equals S. Now what is S? It's the Laplace transform of a time derivative. All right, and so the magnitude in dB is 20 times log S, which S equals j omega, and we have 20 times log the magnitude of the real squared plus the imaginary squared, which gives us 0 squared plus omega squared. Now, sometimes people make a mistake with this imaginary part, where if I had a complex number 1 plus j, I'd have 1 squared plus 1 squared, which equals about 3 dB, not 20 log 1 plus j squared, 1 squared minus 1, which is the log of 0 is undefined. The imaginary part just strips that number next to the j and puts it right there. So you don't worry about j squared or anything like that. So what we get here is 20 times log omega. So in this case, it's easy to start at omega equals 1 because log of 1 is 0. Then omega at 10, right, is log of 10 is 1 times 20, and I get 20 dB here. Log of 100 is 2. 2 times 20 gives me 40 dB. And really, you can just put your marker right here at 0 and draw a line and put slope 20 dB per decade, and it goes it goes 20 dB per decade. You can never really have 0 radians per second. You can get very close, but when we get into it later, you'll see that it doesn't really work. So that is the magnitude of S. What's the phase? Well, the phase can be found by looking at the S term, which is j omega divided by 0. And you might say, well, wait a second, that's some kind of weird infinity thing. No, that 0, the real part being 0, yes, the real part is 0. So it doesn't exist. So there's only one thing going on here, and that's the imaginary part. And no matter what it is, the phase is always 90. So 90 minus 0 phase is just 90. And you can also look at it, the arctangent function. So no matter what the frequency is for a 0 at 0, it's 90 degrees. Now let's look at a pole. Right, we have the transfer function is 1 over s, and yep, 1 over s is the transfer function of a step function or the Laplace transform of time integration. We go through the derivation. The real part is still 0. The imaginary part is just omega squared. Simplify, we have 20 divided by 20 log 1 over omega, which is minus 20 log omega, and we have a line with minus 20 dB per decade. What about the phase? Well, in this case, we have a real part on top, so it's 1 at an angle of 0. Then we have j omega here, which is omega, that's 90, not 0, 0. So we have 0 minus 90 equals minus 90 degrees of phase. Remember, when we're dividing magnitude and phase form, we divide the magnitudes and we subtract, we find the difference between the phases. So again, that's 90. Here's a more formal way of looking at it, but the numerator, right, I have one real component. The imaginary part is 0, so the phase is always 0. Over here we have a 0 real component, and the imaginary component is omega. It keeps increasing, but still it's always 90. So 0 minus 90, minus 90 degrees of phase. So let's just summarize what we have so far. A Bode plot consists of magnitude in dB and phase, preferably degrees, of a transfer function. It's both. So if you do a Bode plot on your exam, you need to have magnitude and phase. All right. What do zeros do? They make the transfer function go to 0. So that's the numerator polynomials going to 0. We add a line with 20 dB per decade on the magnitude plot if the frequency is high enough. And I'm going to explain that a little bit later. And we add plus 90 degrees of phase on the phase plot, again, if the frequency is high enough. And for poles, they make the transfer function go to infinity. Right? The denominator goes to 0. And we add a line with minus 20 dB per decade on the magnitude plot, again, if the frequency is high enough. And we add minus 90 degrees of phase if the frequency is high enough. Now, what do we mean by that? Let's do it with an example. Let's find the magnitude of 1, 0 at minus 1 radian per second, or a transfer function that equals s plus 1. All right, now we have 3 cases to do our hand plots. When omega is a lot less than 1, when it's equal to 1, and when it's greater than 1. So we still have the same function here where we want to find the magnitude of this transfer function, which is the square root of 1 plus omega squared. But because omega is a lot less than 1, we can set it to 0. So 20 times log of 1 is 0 dB. Now when it's equal to 1, we get 1 squared plus 1 squared, which is the square root of 2, which is about 3 dB. Then when omega is a lot greater than 1, this term is so much greater than that term that we get the square root of omega squared, which is just 20 times log omega, which we get our line of 20 dB per decade. So before, when we had a 0 at 0, we just had a line here. But now the frequency has to be higher than the critical or the cutoff frequency. In this case, it's 1 before we see that line. Before then, it's 0 dB. What about the phase? So again, we've got, before we get to the phase, we'll do the magnitude. So when we can see that we plot it 0 dB right up to the critical frequency, and then we see our line of 20 dB per decade. Now here's the thing. This is really plus 3 dB, but when we draw these asymptotic plots, we keep it at whatever the gain was before the the 0 takes over. Okay. Now we'll do the phase. Now we still have 3 cases. When omega is a lot less than 1, we have approximately the arctangent of 0 divided by 1, which is it's all real, no imaginary, 0 degrees phase, right? Then when omega equals the cutoff frequency, right? We have 1 divided by 1 in this case, which gives us 45. Then when omega gets a lot bigger than 1, we are getting this infinity divided by 1, which is 90. Now the way to plot this is when you're at the critical frequency, and in this case the critical frequency is 1 radian per second, you go to 45. When you're 1/10 of the critical frequency, in this case 0.1, you're at 0 degrees phase. When you're at 10 times the critical frequency, and in this case 1 radian per second, you go to 90 and never come back down. What about when we have a 0 at minus 1 radio per second, which is a pole? We have our 3 cases. When omega is a lot less than 1, if you go through, we find out that we're still left with 20 log of 1, which is 0 dB. Now, why is that the case? Because this critical frequency of 1 is also right here. So when S equals 0, 1 divided by 1, we get 0 is 1, which gives us 0 dB. When omega equals 1, or the critical frequency, we just get 1 over the previous relationship, 1 divided by the square root of 2, which is around minus 3 dB. Then when omega is a lot greater than the critical frequency of 1, we get our line with a negative slope of minus 20 dB per decade. So when we're looking at this pole, we come right up to the critical frequency of 1. Even though we know it's minus 3 dB, the way we plot it by hand is we keep it at 0 dB. Then we just draw our line and we go down 20 dB for every decade. All right. The phase, much the same way, is that we always have 0 degrees in the denominator, and so we'll have 0 degrees in the numerator as well, and so the 0 minus 0 is 0. Here we have 0 minus 45, which gives us minus 45. This gives us plus 90. 0 minus 90 is minus 90, and you see the plot that we have here. So the critical thing to remember is that at the critical frequency, and in this case we've chosen an easy value of it equal to 1, we're at minus 45 degrees because we're equal to each other, right? Just draw the vector. At 1/10 the critical frequency, we're still at 0 degrees phase. And at 10 times the critical frequency, we're already up to 90. And then we don't come back down. Now, when you're plotting this, yes, this does curve some. If you were to do it in LT-Spice or plot out every point numerically, you would see it. But for an asymptotic plot, this is what we would see. Now let's try to summarize this. So if I just had the transfer function equal to S plus omega c, in all these examples omega c was just 1 radian per second, but I raised it to the factor of n, what that means is there's n zeros at omega c. The magnitude would be 0 dB until this cutoff frequency. Then the slope of that line would be the number of zeros times 20 dB per decade. The phase, still 0 degrees until the cutoff frequency divided by 10. But then at omega c, it would be n times 45. And then when you were at 10 times omega c, it would be n times 90. All right. Now what about poles? Well, this could be a low-pass filter. We have omega c to the n, and that's kind of critical because it's not always 0 dB. If this and this don't cancel each other when s equals 0, then the gain will not be 0 dB for low frequencies. But bottom line, for this formula, it's 0 dB until the cutoff frequency, then the slope of the line is minus n, 20 dB per decade. For the phase, we start off at 0 degrees. When we get to the cutoff frequency divided by 10, right? Then when we're at omega c, it's minus n times 45. When we get to 10 omega c, it's minus n times 90. Now this is just enough to get you started. It's you really probably want to see the next video before you start plotting more complex Bode plots.